This example comes out of section 1.5, velocity and other rates of change. So we start off with this scenario. We're dropping a ball, and in the book I think they say they drop it off of a CN tower or something. Its distance fallen in meters after t seconds is given by this equation, and they use s for distance or position mainly because I think d gets used for a lot of things later on when we start to do derivatives. We have d's all over the place, and so I guess d is not a good variable for us to use, so somebody decided, oh, we don't use s for too much, so we're using s here. S equals 4.9 times t squared, so s is a function of time. The question we're going to be asked is two parts. So we're asked two quite similar questions, but the first one is what's the average velocity between 3 and 4 seconds, and then the second one is what's the instantaneous velocity at time equals 3 seconds. Average velocity is a bit of an easier question because you have 2 points. So basically, average velocity is going to be my distance after 4 seconds, so like f of 4 minus f of 3 divided by 4 minus 3. In other words, the distance it traveled divided by the time it took to do that. So I can have 4.9 times 4 squared minus 4.9 times 3 squared divided by 1 second. And we find that this thing traveled 34.3 meters, and it only took 1 second to do that, so the average velocity for that second was 34.3 meters per second. Not really calculus per se, just finding the slope of what would be a secant line on that graph, where we've got a parabola and we're finding the slope between 2 points. Now instantaneous velocity is a little different because we don't have 2 points. We have one single point there, and basically we're looking for the slope of that tangent line. In your book they go and they find the value that we did above, so for a bunch of different time intervals, and they find the slope of the secant lines as those time intervals get smaller and smaller. So for example, from 3 to 4 seconds, we just found that the average velocity in meters per second was 34.3. And I said, well, let's make that time interval a little smaller, some from 3 to 3.1 seconds. And they did the same kind of calculation up above without showing all that work, and they got a slightly smaller value, 29.89 meters per second. 3 to 3.01, and a similar calculation, 29.449. It's just crunching numbers at this point. 3 to 3.001. Now we're talking about a very small time interval, a thousandth of a second, and we find that the average velocity for that thousandth of a second was 29.4049 meters per second. We could also try 2.999 to 3 seconds to try to estimate what this limit is, but because I've got a decimal here, it's not immediately obvious. It looks like 29.4 something meters per second is my instantaneous velocity at 3 seconds. But if we go back to what we learned in the last section and do a limit, we should be able to actually find this a bit more accurately. So if I say, what's the limit? Remember that the slope of the tangent line is limit as h goes to 0 of f of a plus h minus f of a over h. Now in this case the limit as h goes to 0 of f of 3 plus h minus f of 3 over h. So what does that look like? It means 4.9 times 3 plus h squared minus 4.9 times 3 squared divided by h. So I do have a little bit of work to do to figure out what this is. If I'm going to expand this out, I could save myself a little bit of work by factoring out the 4.9 so that I don't have to have such ugly numbers as I go along. And I've got 3 plus h squared, which is 9 plus 6h plus h squared, and then minus 3 squared, which is 9, all of that over h. Now good news is that 9 minus 9 is 0, and I have the limit as h approaches 0 of 4.9 times 6h plus h squared, all of that over h. Do a little factoring on top to realize that you've got another common factor there, which is the h. 4.9 h times 6 plus h over h. Those h's top and bottom can cancel, and you can realize that this is just 4.9 times 6, which gives you 29.4 meters per second. So without doing a whole bunch of estimating and guessing and using decimal numbers closer and closer and closer to 3, we do the limit, we find the slope of the tangent line, and it is 29.4 meters per second, meaning if somebody grabbed a radar gun and flashed it on this ball at t equals 3 seconds, this is the velocity that they'd find.